My name is Dr. William Benzing and I am a semi-retired geophysicist hunting for subsurface, geologic hydrogen. My hunt uses the presence of nano magnetite crystals as an indicator or footprint that geologic hydrogen is in the subsurface neighborhood. Let me explain why I am tracking geologic hydrogen using nano magnetite. About 20 years ago, I was involved with deepening an existing well in Oklahoma. The well was originally drilled to 5,000 feet and extended to 7,000 feet. The extension was drilled to test the possibility of trapping hydrocarbons in an overturned, recumbent fold. Several porous zones within a thick carbonate section were identified from well logs, and each zone was tested for hydrocarbons by swabbing back formation fluid into the drill pit. The tested zones were determined to be unproductive. When swabbed, each of the tested porous zones would easily give up a very black cloud of salt water that looked like oil upon entering the drill pit. However, given time, the black cloud would settle to the bottom of the drill pit, forming a black layer in the bottom of the drill pit. The black material at the bottom of the drill pit was magnetic and could be separated from the salt water using magnets. In this slide, I am using magnetic separation to recover the magnetic material. When the black material was recovered and dried out, a very fine black powder was produced. Because it was attracted by a magnet, it was assumed to be ferromagnetic magnetite particles small enough to move freely in brine-filled, carbonate rock porosity. I had never encountered or even heard of this situation before in my 25 years in the oil patch. Because of my curiosity, I decided to determine the purity of the powder and size of the particles. Using X-ray diffraction, the black powder was shown to be very pure magnetite. Fe3O4. Using a scanning electron microscope, the magnetite particles exhibit an octahedral crystal shape, with sizes ranging from 20 to 50 nanometers. This was a surprising observation. I always thought pure nanoparticles had to be created in a controlled, hyper-clean, laboratory environment. These natural, magnetite nanoparticles are extremely reactive antioxidants. In the presence of 3% hydrogen peroxide and at room temperature, they readily decompose the solution into water and oxygen. These particles can play many different roles in redox chemical reactions. Now that the nanoparticles I recovered from a carbonate rock 20 years ago have been certified in terms of purity, size and redox activity, let's add 20 years of advanced, geochemical research and see how they could possibly play a role in hydrogen exploration. When hunting hydrogen, active geothermal areas are natural hydrogen generators, creating hydrogen by the process of serpentinization, where hot water and iron-rich carbonate rocks produce magnetite and hydrogen gas. Is the abundant black deposits found around geothermal springs magnetite? The AI overview says yes. The black material often found around hot thermal springs can be magnetite. Magnetite is a naturally occurring iron oxide mineral, and its formation can be linked to hydrothermal activity. Is hydrogen gas produced in geothermal springs? Yes, hydrogen is commonly found in thermal springs. In fact, some research indicates that hydrogen is often enriched in these springs and can be a primary source of energy for certain microorganisms. Is the magnetite found around thermal springs nano-sized, less than 100 nanometers? Yes, magnetite can be found in nano-sized particles around thermal springs, particularly in hydrothermal environments. In fact, many studies focus on magnetite nanocrystals produced in these settings. There has been some debate as to the source of the hydrogen during the serpentinization process. Some believe the mineral olivine is the source of the hydrogen and that magnetite acts as a catalyst to enhance in the hydrogen generation during serpentinization. Recent research suggests that the magnetite is the primary source of the hydrogen and that olivine and hot water can produce magnetite and the mineral serpentine, with the magnetite producing the majority of the hydrogen. Recent laboratory research supports this concept. This bar graph shows experimental hydrogen production for low and high temperature magnetite, iron-rich granite and olivine. Although pressures, temperatures and cook times vary, all things considered, magnetite outperforms olivine in hydrogen production. The following PowerPoint shows how to build a geologic hydrogen prospect utilizing conventional considerations in oil and gas exploration, such as source rock, migration, trapping and reservoir sealing. Begin with a dry, exploration hole. Locate an iron-rich dolomite formation in the hole that produces a black, nanomagnetite-rich brine from porous and permeable zones when swabbed. The carbonate is the hydrogen source rock. The gas saturation is low due to up-dip migration of the hydrogen away from the well due to buoyancy. When shut in, the well may produce insignificant amounts of flammable, remnant hydrogen at the well head. After locating a nanomagnetite-rich dolomite formation that produces no significant hydrogen gas, consider the well as structurally low to a major hydrogen accumulation within the same dolomite formation. Review the geologic, geochemical and geophysical data to produce an up-dip structural closure that will trap the migrating hydrogen gas within the dolomite formation and produce a significant hydrogen reservoir. In this case, the structural closure is formed by a low-lying recumbent fold that can occur on the backside of major crustal uplifts such as the Wichita Uplift of southwest Oklahoma. After locating a structural closure, consider the sealing capacity of the structural closure. Because of hydrogen's small molecular size, low molecular weight and high diffusivity, it can permeate many materials including some shales. Four-way closures are preferred to faulted closures since fault sealing may be problematic. The seal for this hydrogen reservoir is a thin granite cap rock formed by an unconformity after structural uplift. The granite is tight as a drum because of the ductile shearing in the fold limbs that occurs during uplift and folding. The ductile shearing dramatically reduces the porosity and vertical permeability within the granite. If you are interested in exploring for subsurface hydrogen and think the preceding hydrogen prospect would be worth testing, you will be glad to know that the conceptual prospect just presented is, in reality, a real prospect that is available for testing with estimated recoverable hydrogen reserves of 53 BCF valued at between $250 and $500 million. As shown in this PowerPoint, the prospect is called the Smoking Gun Hydrogen Prospect. The word footprint has been changed to Smoking Gun. The prospect advertisement, shown here and on YouTube, reads as Nano Magnetite, the smoking gun that can be used to locate shallow, white hydrogen in the earth. Let's drill and find out. The next PowerPoint is a familiar prospect cross-section used in the YouTube video. This geologic cross-section displays an eroded, recumbent fold in southern Oklahoma. The iron-rich, carbonate rock that contains magnetite has been folded over to form a structural trap that has been sealed by a thin granite layer. The hydrogen gas that has been generated within the iron carbonate has migrated updip to form a reservoir. The down-dip well that I participated in and observed the dispersed nanomagnetite intercepts the iron-rich carbonate at a level below the gas-water contact of the reservoir. The presence of a hydrogen reservoir, sealed in granite, can be tested by drilling an updip, 5,000-foot test hole. The top of the granite has been established by shallow and abandoned natural gas wells which stopped drilling upon encountering basement rock. The photographs below the cross-section clearly demonstrate the presence of large, low-lying, recumbent folds in basement granite and metamorphic rock. The exact thickness of the granite cap rock has not been determined, but it is estimated to be several thousand feet or less. I am looking for a company or university to closely work with in order to test this novel hydrogen prospect. I have a doctorate degree in geophysical sciences from the University of Chicago and 20 years exploration experience with Conoco. Financially, I would like to recoup my portion of the dry hole costs in the down dip well. If interested, please contact me at cancerout@ymail.com. Thank you for your time in viewing this presentation.